Hello, thanks for joining me again to learn a little bit more about energy models. So last time, I gave myself a challenge to energy model a basic house I designed in 30 minutes. And today, I'm going to run you through how to analyze the results and use the results to make some informed, effective decisions to improve the energy efficiency of this house in another 30 minutes. But before I jump back into the model, I just want a quick recap on why I do this and why I filmed this two-part series to promote energy model in the first place. If we look back, it's just like any technology. When it first introduced to the market, that any technology is expensive. Very few people know how to do it. So the professionals will spend a lot of time just to figure out how to make it work. And just like energy model is no different. But in the last probably 10 years, we start having more and more and more, not just pioneers, but early adapters to figure out and streamline all the systems and process of energy model. And then now we really have a really strong foundation for more professionals to adapt this technology and extract a lot of value in a much relatively short period of time. So the way I see it is I truly believe right now is kind of the tipping point for energy modeling from having just a few early adapters to an early majority of designers, architects, group home builders, and other consultants to start benefiting from this technology and process to enhance their design and building services. So basically, that's why I hope my two-part series will at least help a few people and then encourage more people to do energy model and at least give it a try because there's really nothing to lose. But now let's jump back into the model and let me share my screen first. All right. So again, just start with a quick recap. Last time I modeled this building based on New Zealand Building Code H1 minimum standard. So the high-level result shows the heating demand will be around 142, total electricity demand 125, overheating 3.6%. And before I start analyzing the results, it's always a good practice to check whether I have made any critical mistakes first. And the easiest way to do that, instead of going through every single input one by one, I'll just go to the Homestar results here. So, oh no, immediately Echo is telling me I have some data missing. Potentially I'm missing the whole ground floor. So let's check out what I have done. So now I'm going back to the areas. So I'm going to scroll down. These are all the walls. They all look fine. The roof is looking fine. So here I do have a floor to outside. So it is an external floor. But here, that just reminds me that Echo actually treats the ground floor slab or the suspended floors differently to any other floor to outside. So this is a mistake I made, and then this could cause a little bit of difference. So the next step I need to do is I firstly need to delete this floor by making the quantity to 0. And then I'm going to add another real ground floor. So slab on gray, 94, and the assembly is floor 1. In this case, I don't have underfloor heating, so I don't need to tick this last box. So I'm going to create a new real ground floor, and then I have deleted the original floor to outside. So the heating demand does drop a little bit once I corrected this mistake. Also, the overheating dropped a little bit somehow. And the reason why it has this result is because, at least in Queenstown, it's quite a cold climate. So the ground temperature on an annual basis is normally higher than the air temperature. So previously I had a floor to outside, which means more heat loss because the air is colder. And now I place this floor on the ground, which is warmer, and therefore I have slightly less heat loss. So now I've fixed this mistake, which is good. I'm now going back to the result, and hopefully, yeah, there's no warning sign anymore. But given that last time I have rushed through the whole energy model in 30 minutes, just for safety, I do want to have a quick check whether I have made any other mistake. So like I said, I wouldn't be going through every single input one by one, but I'll definitely have a browse through some of the impactful item. And in most cases, the most impactful items are, other than the thermal envelope, they will be the windows and potentially ventilations or heat pumps. So I'm just going to have a quick check at all the window input I have made. So again, now you can see some of my poor practice because I rushed through the model in 30 minutes. I didn't really name my windows, so it's a little bit harder for me to navigate now. But again, just have a quick look at all the framing types. Is all aluminum, thermally broken mostly, other than the door between the hallway and the garage here. So the frame is looking all good, but the glazing type, let's have a look. Yeah, there is probably something wrong here because as a designer, I do remember I probably only have 2 external doors instead of 3, but I can see 3 standard door panels being selected here. So let me see, there's window 10, window 10-2. So if I look at the size, yeah, 1 meter, 0.3. So the -2 is definitely the side light of the front door, which really should have a glass instead of a standard door. And of course, when we have a glass, there is 2 ways. There is solar gain all of a sudden instead of a solid panel, and then there is heat loss to that. So that's definitely a mistake I have to fix. Although by looking at the result, it's the impact is not significant. Yeah, overheating 2.4 to 2.6, the heating demand almost doesn't change. But anyway, that's one less mistake. And ventilation, air tightness level 5 at 50 Pascal. Building code minimum standard doesn't require any mechanical ventilation other than intermittent fans. So this is all looking correct. Now, I have a little bit more confidence on the quality of the model I have put together. And so now I can start analyzing the result finally. So to analyze the result, of course, we go to the results page, and then you can see there are several blocks of different results. For example, dwellings, energy, and carbon, heating demand, as you can see here. And then down there, you have the cooling and overheating. On the right-hand side, you have the heat balance chart. So I'll just quickly take you through those numbers. The first one is annual heating demand, which is probably the most straightforward number. Basically, the passive solar design and the quality of the specifications, these two together informs the space heating demand. And just based on my years of modeling experience, especially in Queenstown Lakes District, the worst kind of building code minimum spec and the design I have modeled in since the new H1 was introduced was probably around 180 for the heating demand, and the best example is probably around 110. So this particular design, I'm sitting at 130. That's probably meaning that's above average, although it's actually not the best solar design, passive solar design example. And the next one, the annual electricity demand. Different from just the heating demand, the annual electricity demand includes hot water and lighting. And now you can see the number, the demand is 117, and that's slightly lower the heating demand. So now your question, how can we have the heating demand already sitting at 130, but the total demand is less than 130? And that's because the total electricity demand is not looking at just the heating demand itself or hot water demand itself. It also multiply by how efficiently we can fulfill those demands. So if we try to fulfill the heating demand by using diesel heater, that's probably not a very efficient example. But on the other hand, if we use a very efficient heat pump that delivers an annual COP on 3.5 on average, that means that heating efficiency is almost 350% compared to, say, a panel heater. And that's how we can, how we see that the total demand might often be lower than the heating demand itself, as long as we use a good efficient heat pump. In this case, we do use a good single heat pump to cover 50% of the space heating. So if we scroll down a little bit, so this heating demand basically is the closest indicator of winter comfort for the occupants or for the users. And the total electricity demand is the closest indicator to the final power bill people actually pay for. So sometimes we can have a slightly larger heating demand, but a pretty low annual electricity demand if we use a very efficient heater for both the heating and hot water. So there are just different mechanisms we can push or pull as an energy modeler to try to figure out the most effective way to lower people's power bill. So if we scroll down here, that's the overheating result, which is a very hot topic, especially in recent years. So the first one you can see here, the summer window ventilation rate. This indicates how many opening windows I have allowed for, including cross ventilations, which I entered those data in the ventilation worksheet previously. And in this case, I have allowed for 0.5 air change by using opening windows, and obviously we all know opening window help reduce overheating. And as an experienced energy modeler, my recommendation is never allow for more than 0.5 air change. Otherwise, you will over rely on just opening the windows to counter overheatings. And there are many reasons why people might not wish to open the windows during certain time. But anyway, the next one to it is the overheating, and in this case is 2.6% after I fix that little mistakes. So that's looking not bad. In general, I think anything under 3% is more than acceptable, but obviously overheating is never considered as a good thing. So now we understand these few fundamental important parameters in the energy model. We can finally start looking at this beautiful, colorful thing that's called the heat balance chart. So the beauty of the heat balance chart is it outlines all the sources of heat loss from the house, and then all the sources of heat gain. And then the criteria is the energy model will assume these two are balanced in order to keep the house at 20 degrees is the ideal heating recommended by the World Health Organization. So the way I would normally look at this heat balance chart is, okay, tell me which is the longest bar. In this case, the highest or the longest is the heating demand, right? So we have quite a large heating demand, 130 is just sitting there. And the heating demand we need to pay for, is much larger than the solar heat gain, is even larger than the solar heat gain and internal heat gain combined. So this kind of just tells us, if we don't do anything else, we probably do need a very efficient heater, because the demand is so high. We have to fulfill that efficiently in order to manage the operational cost. But if we do want to reduce the demand fundamentally, instead of just relying on efficient way to compensate that demand in some way, then this heat balance chart can immediately direct our attention to what's effective. So in this case, we can see three really large sources of heat loss. One is ventilation. This includes air leakage. The second one is the windows. And the last one is the external walls. And this is really no surprise, because building code only require us to use 90 framing and R2 for the insulation, right? So yeah, so this is basically the most important analysis we need in an energy model. Is that there is really nothing more important. We understand the highest bar, whether it's heat gain or heat loss. If the heating demand is really high, we focus our energy on, yeah, we do need a very efficient heater. And to reduce the heating demand fundamentally, it already highlights, okay, these are the three things. In this case, we need to pay a little bit more attention to reduce the demand effectively, and probably don't waste time on other items unless we want to. So having this knowledge now, the next step for me is just simply going to look at what wall and windows and ventilations I have used, and whether there are effective way to improve them. So given the external wall is the largest source of heat loss, that's what I will look at first. So I go back to the area worksheet. So yes, I do have quite a bit of external walls. And then the R value is only 1.91 in this case, in reality, when I assume 30% timber content in the 90 mil framing. So if I were to try to improve it, there are several ways. Maybe we use a very much better insulation, but normally it's much more expensive, or we try to use 140 framing. So in this case, 140 framing is actually pretty standard nowadays. So that's the first thing I will try and see how it goes. So wow, the difference is actually quite massive. The heating demand is now reduced from almost 130 to 113, right? So it is an effective way. But if we look at the R value, you'll notice that it's only increased from 1.9 to 2.77. It's probably not as big as what we would expect. And the reason for that is just timber content, really, because with the 30% timber content is obviously not a good insulator compared to an insulation material. So every time we increase the insulation, the timber basically more heat is gonna try to go through the timber instead of being stopped by the insulation, and that's why optimizing the timber content can sometimes be really important, and also the more timber we use, the more expensive the framing will be, right? So it's kind of a win-win scenario if we can optimize the timber framing by reduce unnecessary studs and sometimes by reducing the duans. This could altogether be done quite effectively. So in this case, I'm just gonna be optimistic. I know I'm going to give my friend and trust designer a call saying, hey, can you do better? And then work through that option with them, which is pretty standard with ITM and placemakers nowadays. So I'm going to try only 20% timber content instead of 30, and then I'm gonna save it. So as you can see here, the R value has jumped from 2.7 to 3.2 basically, and it's now looking much better compared to the original 90 framing. And then the heat loss obviously reduced even further. And the next one I'm going to look at is the windows. The reason why I probably look at the window before the ventilation from just an energy performance perspective is because window governs not only the heat loss, but a lot of the heat gain. In fact, 90% of the heat gain is often going through the window. To be more specific, the glazing part of the windows. So I don't know if you can remember, but on the result page, the heating demand was is currently larger than the free heat from the sun, right? So in this case, we know Queenstown is still considered a cold climate. So if there is a way for us to increase that free solar heat gain, it will more likely to be a positive thing. Although the overheating is always something we need to be quite careful of. So let me just go through the glazing options I have here. So in this case, the current default option, which basically reflects the industry default or industry standard, it says the G value of 0.54, which means it allows 54% of the total solar radiations into the house, and it filters out 46%. So I'll say this is probably a little bit too much for Queenstown climate. So let me see if I can find another double glazing option that will give me a little bit higher solar gain without compromising the insulation. So in this, I can see here there is AGP Solux E glass instead, and then having the coating on surface 3. So instead of the industry default to have the coating on surface 2, by coating that film on surface 3, it actually increased the solar gain. So let me just try on one window first and then see what it does. So here we go. I can see the heating demand is dropping even further, while the overheating does go up a little bit. So I do need to be quite careful to find the right balance here. But given the fact we know the heating demand currently is still quite massive, I'll say I will try to make a trade with the devil for now, and then trying to manage it somehow. I'm going to use the same glazing on all the windows. Right. So now we are looking at the heating demand at around 104 and the overheating around 4. So overheating is not much higher, but slightly higher. We probably do need to find a way to bring that down a little bit. And the third item we need to look at is the ventilation as informed by the heat balance chart in the result page. So as we know, if we use the building code as the baseline, there is basically no requirement for mechanical ventilation other than the intermittent kitchen and bathroom fan only if people do decide to turn them on. So basically, in any building, I will always suggest and almost treat having a mechanical ventilation running 24/7 as the non-negotiable. That's for two things, basically the health of the people and the health of the building itself. The social return on investment and or the long-term financial return on investment definitely still outweigh the cost of having a ventilation system. Yeah, overall, like having ventilation it's just the effective way to keep any house dry, and then dry house is also easier to heat, and then ventilation also remove CO2, for example, which having fresh air supply and stale air removal just improve the sleep, improve the productivity, etc. You name it. So in this case, again, Queenstown is a cold climate, so I will probably allow for a heat recovery ventilation rather than just continuously extracting system. So I'm just gonna pick Mitsubishi Losney in this case for the easiness of it. And here it also requires, once we have an MVHR, we need to pick whether it's inside or outside the thermal envelope. In this case, I think the space I allocate for the Losney is actually in the garage, which is definitely not as cold as the attic. It is under the ceiling insulation. It is in the temporary climate in the cupboard. So it's not bad, but unfortunately it's still outside of the thermal envelope. And then it does require me to enter the duct insulation. So, well, all the ducting will be insulated by, say, 15 mil. And in this case, I have designed the ducting to be very, very short. So in this case, I think it's really just about 2 meters in total between the MVHR and the thermal envelope in this case. And one of the beauties of having a mechanical ventilation system is suddenly we have a fan we can control. So if we wanted to ventilate a little bit more during summer to help mitigate overheating, we can do that quite easily, instead of saying, okay, we need to open windows a lot more every single morning in summer. And we just set the machine at a slightly higher rate. So in this case, I'm going to give it another 0.5 air change in summer, and then that itself already help us to reduce the overheating even further back to the original, while we reduce the heating demand very, very dramatically. So now if we look at the result quickly, we managed to bring the heating demand down from around 130 to 85 by literally changing three things. I have to be honest. We use 140 framing. We introduce heat recovery ventilation. And the third thing is free, because we only just specify a different low-E glazing that doesn't cost any money. So I'll say those few actions are probably quite effective and will most likely give us a good return on investment. Right, so if now is probably the good time to go back to the results. As you can see now on the heat balance chart, I have basically 85. That's 85 kilowatt-hour per square meter. That's solar again. That's free. So, and then also 85 for my heating demand. So now I can proudly say the amount of free heat I'm getting from the sun based on this design is at least the same as the remaining heat I have to pay for. And if we look at the left side, which is the sources of different losses, it's looking a lot more balanced than what it was before we have those really significant sources of heat loss, but now it's much more balanced. And obviously, if we want to go further, we can use PVC window, etc., for example. But obviously, energy model, another point of having energy model is not just making effective decisions on making the building more and more and more energy efficient, it's also trying to make cost conscious decision, right? So I do understand the cost of going to PVC window, and I do encourage it for anyone who can afford it. But in this case, let's stick to what we have now. So if I scroll down, it will say how many Homestar points I can get at maximum. And in this case, it's still saying I can get 0 because I miss a mandatory minimum, which by memory, the annual electricity demand has to be around 84 instead of 91. So that shows I still need to find a way to reduce the total energy demand. And I can either do this by further upgrading the thermal envelope or by using a more efficient heater for either the space heating or hot water heating. So in this case, I know how much it costs to upgrade to a ducted heat pump. I'm not going down that road, but I can probably look at whether I can use a hot water heat pump. And one of those monoblock system only costs around 2,000 to 3,000 more on top of the traditional hot water cylinder. So it's probably gonna be fairly effective, I would say. Let's have a look. So now the result on the top at the top here is showing the electricity demand is dropping from 90 something to 71. So if we go back to the result page, I'm pretty confident now it will be showing we can achieve Homestar 6 all of a sudden. So yeah, it is a good outcome. We basically, even in the harshest climate in Queenstown and based on a design that's not optimal from a passive solar perspective, by upgrading three basic specs, 140 framing, a heat recovery ventilation, and using a hot water heat pump, we can already achieve Homestar 6 standard. And if we compare the difference of the heating demand from 130 down to 85, that's a really good 30 to 40, almost between 30 to 40% improvements compared to the cold minimum standard, right? So yeah, by simply upgrading those few things, we can actually achieve quite a lot already on the energy efficient side. So yeah, this is pretty much the end of how we analyze it and how we identify the issues, how we use energy model to pick the effective upgrades or optimal floor, wall, roof, windows, ventilation, also skip the ones we don't necessarily need further attention or upgrades. It also helps us to pick the effective and efficient heating and hot water system. But there is one last thing, which I actually start using in real life practice more and more, is that under the result page here, if you go down to the H1 November after November 2023, you can actually see a magic button here on the top right corner. And if you click it, Echo will automatically generate an energy modeling report that is suitable for H1 compliance. And I can basically upload this with my building consent application. I have done that a few times. Council always accepted with no question, because this report from NZGBC is structured in the exact way H1 VM1 modeling method requires to fulfill compliance. So yeah, like like what I just did here, 30 minutes to energy model, 30 minutes to analyze the issues, and then at the end of it, I can click the button, and then here we go, good to go for compliance. So obviously, I do have to acknowledge that in real life practice, I probably wouldn't try to rush doing an energy model within 30 minutes. I'll happily allow for an hour, possibly a little bit more, especially for more complex building. But it kind of proves that energy model and using the modeling method for compliance is not only possible, but feasible once you practice, and also the amount of values you can extract within a reasonably short few hours is definitely worthwhile, in my opinion. So thanks for watching, and I hope you learned something from this video. Thank you, and see you next time.